Welcome back. Today's lesson is 2.11 of the remainder theorem for Algebra 2. So the remainder theorem is directly related to polynomial long division that we just did in our previous lesson. All right, it says if a polynomial p of x is divided by a binomial x minus a, then the remainder obtained is the actual value of p of a. All right, so just giving you a little bit of an example with 1, what we're saying here is that if we consider the binomial x minus 2 and we determine what that remainder is, that's going to be the same thing as determining what p of 2 is. So we'll talk about what that means right now, because I think example is the best way to learn. So let's do our polynomial long division and do x minus 2 divided into x cubed minus 4x squared minus 7x plus 10. All right, so now x goes into x cubed, x squared times, which gives me x cubed minus 2x squared. Remember, we change the signs. We subtract. This turns to a plus. I'm going to keep using different colors here, so bear with me. So we get minus 2x squared minus 7x. Okay, because if you're writing things down, sometimes it's easier to watch first. So completely up to you if you want to pause in between. So now x goes into negative 2x squared minus 2x to get a negative 2x squared here, and negative 2x times a negative 2. Remember what we're doing. We did this times this to get that negative 2x squared. Then we did this times this to get that positive 4x, which I'm going to put right here, plus 4x. Let me just erase this so it's not confusing. All right, so we subtract now. We change signs. Change this to a plus, this to a minus. These cancel, and I'm left with negative 13x and bring down the plus 10. I can add or subtract in this case. 7 minus 4 is not 13, it's 11. See, even the best of us. 11x. So x goes into negative 11x minus 11, which gives us negative 11x plus 22. We're going to change those signs again, plus and minus. And that's going to give us a remainder of negative 12. Now, what the remainders theorem says is that if you just consider now, remember, if x minus 2 is the factor, then the 0 associated with that, x minus 2 equals 0, add 2 to both sides, and x is equal to positive 2. 2 is the 0 that's associated with this factor. So this is the 0, or sometimes we call it the root. All right, and what we're going to do is we're going to evaluate p of 2. So that means that's going to be 2 cubed minus 4 times 2 squared minus 7 times 2 plus 10. And my advice is you put this whole thing right into your calculator. But 2 cubed is 8, minus 2 squared is 4, 4 times 4 is 16, minus 14 plus 10, which is equal to negative 30 plus 10, which is negative 10, and negative 10, okay, plus 8. That won't work. So negative 30. Yeah, it's 18 minus 30. All right, so it's 18 minus 30, which is negative 12. So as we can see, the remainder here is equal to p of 2. All right, so let's take a look at a couple more examples. Exercise 2. Consider each of the following scenarios where we have p of x over x minus a. Remember what this means. This means this is the polynomial right here, and this is the factor x minus a. All right, in this case, we're going to be talking about a being 2 in example a being negative 3 in b, and we can check to see if the remainder theorem works out, which of course we know it does already. But we're doing the same thing that we just did up in example 1, in exercise 1. So x minus 2 divided into x squared minus 8x plus 18. And let's not waste time here. Why don't you pause the video and do this yourself? And then in just a second, I'll pop up those answers. So here are the solutions to the polynomial long division for exercise 2a. So this one gives us a factor of x minus 6 with a remainder of 6. So if the remainder theorem holds true, that means that when we do p of positive 2, remember it's always the opposite sign of what we're given in our factor. So here we're going to do p of positive 2. So at this point what we're going to do is we're going to substitute in 2 squared minus 8 times 2 plus 18. And once we put that whole thing into our calculator, it does equal negative 12. Oh, I'm sorry, it does equal 6. I'm thinking about exercise 1. Because you get 4 minus 16 plus 18, which is 4 plus 18 is 22 minus 16, which is 6. We're going to do the same thing with b. So why don't you do the same thing at home? Why don't you set this up, all right, do the math, and see what you come out with as your remainder. And then I'll put the solution up for you. So there you have it. And again, please make sure you're trying these on your own, because it's really important that you understand how to do this. And the best way to understand this is by practicing. So now we're just going to check. Remember, if it says x plus 3 over here, that's our factor. Our root is negative 3. And that's why over here we're going to evaluate p of negative 3. So it is 2 times negative 3 squared plus 11 times negative 3 plus 11. And if you do that whole thing in your calculator, you get 2 times 9 minus 33 plus 11, which is equal to negative 4. Please don't just assume it. Make sure you're checking it in your calculator. Okay, finish up writing things down, and I'll meet you at exercise 3. Okay, so if the ratio was placed in the form q of x plus r over x minus 9, where q of x is the linear function, then which of the following is the value of r? So there's a couple of ways to do this. You can either use the remainder theorem and you can evaluate each one of these. No, you can evaluate, I'm sorry, you can evaluate p of positive 9, or you can actually do the math out and do x minus 9 into x squared minus 11x plus 22. Sometimes people are more comfortable doing it the long way, but remember, we get to the same place. So if we do this, we get x squared minus 9x. We change the signs to minus and plus. So we get minus 2x plus 22 minus 2, which is minus 2x plus 18. Change the signs to plus and minus. and we get positive 4. So our remainder is positive 4. Another way we could have done that is we could have done our, in other words, we could do p of 9 like we did in our first problems and get 9 squared minus 11 times 9 plus 22. All right, so it's 81 minus 99 plus 22, which is equal to 4, which should be the same thing we get right here. So we can use the remainder theorem to tell if a linear expression is a factor of a polynomial because we have to see if the remainder is 0. So that's a really important fact to learn from the remainder theorem. So for example, in exercise 4, it says determine if each of the following are factors of the listed polynomial by evaluating the polynomials. So if we consider, they're saying, is x minus 3 a factor? So we can do this one of two ways. If f minus 3 is a factor, we know that positive 3 is the 0. So we can do 3 squared minus 11 times 3 plus 24, which is 9 minus 33 plus 24. If we add 9 and 24, we get positive 33. So we get 33 minus 33, which is 0. So make sure you're answering the question because the question doesn't say what's the remainder. The question says determine if each of the following are factors of the listed polynomials. So make sure you're taking a moment to say x minus 3, so you can say therefore. You can do these 3 little triangle dots. Therefore, x minus 3 is a factor of x squared minus 11x plus 24. And you can even put a little explanation in there because the remainder is 0. Or the evaluation is 0, depending on which way you determine this. So in other words, you can go back and do it the long way over here, which now you could do the same thing. I could say p of, it's x plus 5, so I would check p of negative 5 to be the 0. Or we can do it the long way and do x minus 5 into 2x squared plus 9x minus 2. So once you do this whole thing out, you get, let's see, 2x here, which is 2x squared plus 10x. We're going to change the signs to a negative and a negative. So we get negative x minus 2. So this is minus 1. Negative x, nope, not minus 5. That's minus 5. Plus. Minus 5. So now we change the sign. Plus, plus. These cancel, of course, and we get positive 3. So this one, the answer is no. This is no. Okay, and again, you'd say x plus 5 is not a factor because the remainder is 3. All right, so now if you did it this way over here using this one, you would get something that does not equal 0. And you could state the same thing. It's not a factor because it does not evaluate to 0. All right, so why don't you try C and D on your own, and I will pop up the answers in just a few minutes. That's right, pause the video right now and give it a try. So there we go. There are the solutions. So take a minute and check your work against my work and see if you agree. Now on the left side, I did it the long way using polynomial long division, and I came out with a remainder of 0. Now if I had used the factor, remember if x minus 1 is the factor and I had used the root, I would have checked p of negative 1 to see if that was evaluated to 0, in which case it would be. All right, on the right-hand side, instead of doing it the long way, I determined if x minus 5 is the factor, then x equals 5 is the root that I was checking. And when I plugged it in, I did not get 0. I got negative 5. So if I had done it the long way, negative 5 would have been my remainder. But either way works fine because the remainder theorem says that you can sort of do it any way you want to. All right? So pause if you need to and write down what you need to finish up. And then we're going to look at exercise 5, which is a great question. So exercise 5 says, for what value of k will x minus 4 be a factor of this? Show how you arrived at your answer. So what I did is I said, well, I know that if x minus 4 is a factor, I know that x minus 4 has to divide evenly into x squared plus kx minus 52. Now, don't get too upset about that kx. We're going to deal with that. So we're going to start the same way that we did before. We're going to say x goes into x squared, x times, right? So do the multiplication, and we get x squared minus 4x. And now we're going to change our signs just like we have before. And then what do we get? These cancel. And I can't really write this, but I can write it like this. How about k plus 4x minus 52? Right? Now, in order for this to be a factor, I know that when I'm done here, I need a 0. So I say to myself, how am I going to get a negative 52 here? So it's a little bit opposite of the way that we were thinking before. So what I do is I take negative 52 and I divide it by 4, and I get 13. So I'm going to try that, and I'm going to do, let's see, plus 13 here, which would give me 13x minus 52. And then I would change the sign and change the sign, and this would be 0. But now I have to pay attention to this piece here. Because if I look at this, I know that, now I have to go off to the side a little bit. I know that k plus 14 has to equal a positive 13. Because once I change the signs, that turns to a negative 13, which means they would cancel out to 0. So minus 14 from both sides, and k is equal to, no, that's not right. Hold on. Am I thinking this right? No, silly me. I wrote k plus 14. It's k plus 4. I know that k plus 4 has to be positive 13. All right, so now that makes more sense. So minus 4 from both sides, k equals 9, and that is right. Now, you can go back and check it again. You can put a 9 in place of the k up here, and let's see if it works, all right? So if we put a 9 here, then instead of k plus 4, we're going to get 9 plus 4, which is 13. Let's use a different color so we can see this. So this becomes a 13, and now everything does go to 0. So k equals 9. Very Common Core kind of question. I like it. All right, because it really tests whether you understand what it means for x minus 4 to be a factor. All right, so that's it for today. We're going to get started on that independent practice, whether we do it at home or whether we do it in school, in class. It's really a good idea to always just take a minute or two and do a few of them and see if you understand what the lesson is teaching you. Okay? So until next time, like I always say, make good choices because we care about you here at PHS and we want to make sure everybody stays safe. All right? Bye.